having Professor Yanofsky's talk. So if you'd like, please help yourself to some food, grab some drinks, and settle down and enjoy this very interesting talk.
Perfect. Thank you. Okay, so I'm going to leave out the microphone simply because I like to have my hands free, and I'm going to talk from here. I don't stop anyone from eating. Eat all you want. You can eat during class, whatever. Okay, so I just picked this topic, the P versus NP problem. It's something that I teach in some of my classes, and you'll see later on which classes. It's considered the hardest problem in computer science. So I think it's an interesting problem. A lot of computer majors, until they're seniors, they don't really see this, but they hear about it. So I just thought I would do it. And louder? You're okay?
Want to use the mic?
No, I don't want to use the mic. Unless, do you hear me?
Yeah.
Okay, good. So I yell during class, I'll yell now too. Okay, so it's called the P versus NP problem. That's my name. My daughter helped me with some of the cooler graphics, and this is the Brooklyn College Computer Club. Okay, good. Well, thank you for inviting me, and I strongly recommend the Computer Club to have more and more events as much as possible. I told you yesterday when I was a student in Brooklyn College, we had a computer club. It was very active. We did a lot of things together. It's a very important thing to do, and it's a great thing. Okay, good. Okay, so let me just tell you what we're going to do. So this is the abstract. The P versus NP problem is considered one of the hardest unsolved problems in computer science. The question basically asks if there exists tricks to solve very hard problems. So I have to explain to you what those things might mean. We will explain what P is, so it's P versus NP, so I have to tell you what P is, I have to tell you what NP is, and what the problem is all about. We will describe two possible ways of solving the problem, okay? And consequences of solving the problem will also be discussed. So if you've taken theoretical computer science or you've taken analysis of algorithms, you might have seen some of this, but if not, whatever. I do have 1 or 2 slides with my own ideas in it too. Okay, so the agenda, what are we doing? I'm going to talk about some easy problems. We're going to call that P. I'm going to talk about some hard problems called NP. This is not working perfectly. Okay. How are they related? What is the P versus NP problem? How to solve the P versus NP problem? I'm expecting you guys are coming up with a long winter break. I think this is a good thing to do to actually solve the problem, and you'll make some money if you do it also. Okay. Okay, so let's talk about some easy problems. Let's talk about adding. This is small, but it doesn't matter. In 2nd grade, you learn how to add, and if you want to add 2 7-digit numbers, you know how to do it. 1 plus 2 is 3. 9 plus 3 is 12. Carry the 1, et cetera, et cetera. So in order to do this, you have to do, if you have 7 digits and 7 digits, you have to do 7 operations. You have to do 7 little additions, okay? And then you get the final answer. We're not interested here in the final answer. What we're interested in is how long or how many operations you have to do in order to get the final answer. Okay? In contrast to addition, multiplication you learn in 4th grade, because multiplication is harder. Let me explain to you why it's harder. Because if you wanted to multiply one 7-digit number and another 7-digit number, what you have to do is you have to multiply this digit times each and every one of them, okay? And then you go and you multiply this times each and every one of them. And then you go and multiply the 2 by each and every one of them. So it's a lot harder. Turns out that is, you do that for this digit, for this digit, for this digit. You add them all up, and you get what's called an n-squared operation. So this is an n operation, this is an n-squared operation. It's a lot more, there's a lot more work to do multiplication than to do addition, and that's why they teach it in the later years. Okay, good. Okay, so let's talk about some other easy computer problems. Addition and multiplication is something computers are very good at, but other things are searching, Okay, and you can do a brute force search. In other words, if I'm looking for a certain person here, what I do is go through each and every person in the room and do that each and every one. Or a binary search. So if I'm looking for something that's ordered, like the Brooklyn telephone book, I would split the book in half and look at half and then split it again and then split it again, keep on splitting it. And that takes only log of n. N is going through all n people. Log of n is how many times can you split it. That's how many operations you have. Okay. Other things we could do is sorting. And sorting could be done in n squared or n log n, etc. Okay, great. Now, another operation another thing that computers can do pretty easy is the following. It's called the Königsberg Bridge problem. And Königsberg is some city in Prussia or Russia, okay? And in the 1800s, they had 7 bridges. It's a city like New York, surrounded by with a bunch of boroughs surrounding a central island. And the island had 1, 2, 3, 4, 5, 6, 7 bridges. I'm sorry, the city had 7 bridges. 1, 2, 3, 4, 5, 6, 7 bridges. Okay, and here's that island. By the way, in that island, there's this church, and this church has, in the backyard of this church is where Immanuel Kant is buried. Okay, he's a famous philosopher. Okay, great. So they used to have this thing that people did in Königsberg, and what they would try to do is they would try to cross every bridge exactly once. They'd try to cross every bridge exactly once and come back to the original thing. And so people tried it. You start here, maybe you go here, have a picnic here, go visit Immanuel Kant, go here, etc., etc. But they weren't able to do it. Okay? At some point, the Tsarina invited a mathematician named Leonard Euler to come to Russia, and she asked him this question. This is a legend. I don't know if it's true or not. And Euler decided to make this. He actually invented graph theory to solve this problem. Okay, so graph theory is about vertices. 1, 2, 3, 4 vertices. There are 4 land masses, and the bridges become edges between the land masses. And then he can ask the following question. Given a graph, tell if there's a path, that means a way of going around, that starts and finishes at the same vertex and that crosses every edge exactly once. Okay? So this was Königsberg's, the thing of Königsberg. So there was a landmass, 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 4 landmasses, and 1, 2, 3, 4, 5, 6, 7. Okay, and now you can look at the problem much easier, not with that picture, and you can try to hit every single edge, bridge, exactly once. And you'll see it's very hard to do that. As opposed to that, let's say we modified the problem and we added in some extra bridges. Okay? Well, let's try to do it here. Go around like this, go around like this, come back here, go like this, up and down, come back here. You started here, you go around all of that. Okay? This has 1, 2, 3, 4, 5, 6, 7, 8, 9 bridges. Okay? So the point is, the 9 bridges of Königsberg is you can do it. Sometimes you can't, sometimes you cannot. Okay? And Euler thought about the reason, hold on, and now we can ask something else. What about this graph? Okay, you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 vertices and a lot of graphs. Now, if you try to do this, can you go through and hit every single edge exactly once, yes or no, and come back to the original place? That's called an Euler problem. Okay, given a graph, can you okay? Now, if you just look at it like this, the only way you know how to do it is try all possible paths. Try this, try that, see if you can do it. But Euler taught us a trick. He said as follows, and it's a brilliant trick. He says, look at every vertex, look at every dot, and see if there's an even number of things coming out and coming out of it. If there's an even number of edges coming out of it. So let's go through it. 1, 2, 3, 4, that's even. 1, 2, 3, 4, that's even. 1, 2, 3, 4, 5, 6, that's even. 1, 2, 3, 4. Yes, they're all even, therefore you can do it. Here, 1, 2, 3, odd. Buzz, can't do it. Okay? 1, 2, 3, 4, 5. Buzz, odd. You can't do it. The point is, if every single vertex has an even number of things, lines coming out of it, then you can do it. Well, now, that makes this very easy to solve. 1, 2, 3, 4, even. Good. 1, 2, 3, 4, even. Good. 1, 2, 3, 4, 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 good. 1, 2, 3. All of these have 4, including down here, and therefore there is such a path. Such a path exists. So Euler's trick is a brilliant trick. He says rather than trying every single possibility, just go through every single vertex, see how many things are coming out, then I'll give you the answer. Okay? And if an even number of edges come out of every single vertex, then there is such a path, otherwise there is none. So Euler taught us this trick, and this trick makes it an easy problem. Okay, so that's an easy problem. Okay, good. So we talked about some easy problems. Let's talk about some harder problems. Okay, so one of the hardest problems is the traveling salesman problem. It's a simple problem. It's simple to state. You can teach it to a third grader, etc. Let's go through it. A traveling salesman wants to visit several cities. He wants to find the shortest path that visits these cities exactly once. In other words, he wants to hit every single city exactly once. He wants to come to a city, sell his stuff, 3 days later, go to another city, sell his stuff, etc., etc. Okay? He doesn't want to go back to one city that he visited already. Okay? Here's a typical example. I put the information here. It's not in geographic order. Here's New York, San Francisco, Chicago, Denver, Los Angeles, Miami. And I give you the distances that you do it. Question, what is the shortest possible route that hits every single city and comes back to it? Okay? So, this is not hard. Okay? I'll just restate the question. For 6 cities, I had 6 cities up there. For 6 cities, you need to try every single possibility. Okay, so try starting here, 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 then try going here, 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 then try going here, here, here. Try all different possibilities. Now, how many possibilities are there? 6 factorial, which is 720. Okay, you have 720 possible routes, and I got to tell you, a modern computer like this can do probably 1 million possible routes in a second, and it won't take that long to do. Okay? So doing it for these 6 cities is not hard at all. Not hard. Takes seconds flat. Question is scalability. What happens if I wanted to do it not for 6 cities, but for n cities? Okay? Well, then I'd have to try all n factorial possibilities. Okay, and n factorial is a large number. So, let's see how large it is. Okay, let's try n is equal to 100. Now, this is not a strange question. Okay, I want to go to the 100 most populous cities in the United States. I want to do it in the shortest amount of time. I want to spend a year traveling around the United States and visiting the 100 most populous cities. Okay, and I want to go, I don't want to use a lot of gas for environmental and financial reasons. I don't want to use a lot of gas, so I want to find the shortest path that hits every one of those 100 cities and comes back to the original thing. Sounds like a nice, what do they call them, gap year project to do in college. Okay, visit the United States. Okay, anyways, if you do it, send me pictures. Okay, so let's see, what is 100 factorial? Well, you go to Google and you type in 100 factorial and you get this many paths. You have to understand, when you multiply by 10, you're adding a digit. So you start off 100 times 99 times 98 times 97 times 96, etc., etc. Each time, you're pretty much adding 2 digits. That's why you have such a giant thing. Okay? So you have this many possible paths. But I told you, a computer like this can check 1 million paths in about a second. So, whoops. Okay? If we have a computer that can check 1 million paths in a second, then we need 100 factorial divided by 1,000,000. That many seconds, because I want to know how long it'll take me, not how long it'll take me to travel around to the 100 cities, but how long will it take me to calculate what the shortest possible route is. Okay? So it turns out to be, if you take that 100 factorial and you divide it by 1,000,000, you get this many seconds, which corresponds to, divided by 60, you get this many minutes. Divided by 60 again, you get this many hours. Divided by 24, you get that many days. Divided by 365, you get that many years. And divided by 100, you get this many centuries. Okay? That's how long it'll take you to calculate what the shortest possible path is. Okay? Now that's mind-boggling. That's 2.9 times 10 to the 142 centuries. That is a humongous number. Okay? The universe will go through a heat death before that time passes. Okay? This is an essential limitation of our ability to know. Okay? We will not be able to know what the shortest path is for 100 cities. Okay? And of course I could ask, what about 300 cities? The numbers become even more astronomical. Okay? So that is a thing. Okay? So that is considered a hard problem. Great. Okay, now whenever I teach this, I always get responses from students. Students always say, oh, don't worry, don't worry. Now I used to get the following response. I used to get, it was like 10 years back, people would say, oh yeah, that's a hard problem, but I have an Apple computer. Steve Jobs is on the, Steve Jobs can do it, don't worry. Okay, nowadays we don't get that type of response. But I do get responses and people tell me, don't worry about it. Okay, the first response is computers will go faster computers. Okay, there are faster computers. I had my first computer when in 82 or something, and I got to tell you, my computer today, or my cell phone goes about 10,000 times faster than my TI-99 4A Radio Shack computer. I love that computer, whatever. Okay, so it's not strange to say, oh, the computers will go 10,000 times faster. In the past 30 years, computers have gone 10,000 times faster. And I promise you, forget about Moore's Law and everything like that, in 20 years, computers will go 10,000 times faster. The only problem is, it doesn't help you. Let me explain to you why. Because if you have a computer that demands 2.9 times 10 to the 142 centuries, then you can get a computer that's 10,000 times faster, and it'll do 1/10,000th of that time, which is only 2.9 times 10 to the 137 centuries. 10 to the 142 centuries divided by 10,000, 1/10,000th of that is only 10 to the 137 centuries. That's the way division goes. Again, these numbers are so humongous that nothing's going to help you. That's not going to help you. Faster computers are not going to help you. Great. The next thing responses that people usually say is, don't worry about it. I'm gonna get, my computer is a duo processor, 7th generation Intel, and I'm gonna split up the problem and do it on a few different processors at the same time, okay? And that will help you very little, okay? Yes, if you take a big problem and you put it on 2 different processors and you parallel process, it will do it in half the amount of time. And if you do it on 10 processors, it will solve the problem, some problems, on 1/10 of that time. These problems are very, very, what are they called, distributive. They're very easy. Or you know what you can do? You can upload it to the web, put out a thing, on Twitter or something like that, and say, okay, everybody download one part, and we'll all separate it, and I'll have 10,000 processors working on this at the same time. So this giant problem will be able to be solved in 1/10,000th of what that is. And of course, we're talking all about these faster computers. Each one of the 10,000 processors are one of these faster computers, okay? Well, that will save you. It'll only take you 2.9 times 10 to the 133 centuries. Okay, again, longer than the universe is going to have a heat death. There's no such thing. Again, that's what it is. 10 to the 137 divided by 10,000 is 10 to the 133. It doesn't help you. So, faster computers are not going to help you. Multiprocessors are not going to help you. Let's just do this. Physicists tell us that there are 10 to the 80 particles in the universe. Not the Earth, not atoms, particles, subatomic particles. Okay? In the entire universe, not the Milky Way, not our solar system, in the entire universe, there are 10 to the 80 particles. I don't know how they counted this number. I assume Mrs. Avogadro helped them. Mr. Avogadro, Avogadro's number. How did they get Avogadro's number? Mrs. Avogadro counted them. That's a joke. Okay? But they got this number. I'm not sure they're correct, but they're probably closer to correct. If every particle in the universe was a computer working on this problem at this speed, it'll only take 10 to the 62 centuries to solve. That's just talking about 100 cities in the United States. If I want to find the shortest path to find 100 cities in the United States, that'll take 10 to the 62 centuries. Again, not every particle is a computer. Not every particle, although some of us believe in panpsychism. No more. Okay. Which means that every particle does have a thing. But it's a cool doctrine. You got to think about it. But it won't help you. Okay? Now, what else? You might have heard the buzz about quantum computers. And you might say, oh, you know what? They're building a quantum computer. The quantum computer is going to save a lot of, et cetera, et cetera. And quantum computers are going to be very fast. So I got to tell you, I wrote a book about quantum computers. It's called Quantum Computers for Computer Scientists. You're a computer scientist. Buy this book. You won't regret it. Okay? And I know how fast quantum computers will help. And yes, they will help. And they will help faster than more than this and more than this. However, quantum computers will only need, instead of 10 to the 142 centuries, you split the exponent in half, it's 10 to the 71 centuries. Okay? So that also is not going to help you. Okay? So again, faster computers won't help you. Multiprocessors won't help you. Quantum computers, if they ever become in existence, will not help you. Okay? What will help you? And I'll tell you. Find a better algorithm. Instead of going through, for the traveling salesman, instead of going through every single possible route, like you did for the Euler, find a trick. Euler found a trick for the Euler problem. How about finding a trick here? Somehow adding up the distances and doing some type of fancy math. Maybe you need calculus 3 to do that. Find a trick that will find the quickest route faster. That would help you. Okay? Problem is, I don't know how to do that. I don't know that trick. Okay? Neither does anybody else. Neither did Euler, probably. Okay? Nobody knows that trick. Which means, I didn't say the trick doesn't exist, which means the trick, we can't use that trick. Okay? Okay. There has been a search for improved algorithms for almost 50 years, probably more than 70, closer to 70 years, 50 years, okay? So far, nothing. Nobody has it. Okay? Better algorithms probably do not exist. Okay? And that's the question. I told you in the beginning. Are there tricks for very hard problems? Okay? That's what the P and NP problem. Question. Do such tricks exist? Okay? But no one proved it. Okay, so let me say this. Better algorithms probably do not exist, but no one has proved it. So there are two answers to this. Better tricks do exist, or better tricks do not exist. Those are the two possible answers for the P versus NP question. Okay? And we'll talk about it a little bit more in a second. But no one has proved either way whether there are tricks or whether there aren't tricks. You have to wait to the end of this talk, and I'll show you how to do it. Okay. Okay, so there are some other hard computer problems, and they're called, all these hard computer are called NP. So the Hamiltonian cycle problem, not the Euler problem, this is a different mathematician named Hamiltonian, deals with the same thing. You ready? Given a graph, tell if there's a path that starts and finishes at the same vertex that crosses every vertex exactly once. Not every line, that was Euler. Not every edge, that was Euler. Now we want to cross every dot. So let's go through it. Okay? Well, let's say we try to do that. Okay? You want to hit every dot? 1, 2, 3, 4. Done. Easy to do. How about here? I even have more bridges. 1, 2, 3, 4. Done. Oh, I missed the middle one. Sorry. 1, 2, 3, 4. Come back. Done. Okay? I don't have to hit every edge. I don't have to hit every single bridge. I have to hit every single landmass here. What about here? What about this graph? Can I make a path that hits every single city and comes back to the original thing? Every single dot and comes back to the original thing. Answer? Ready? I need to tell you what Hamilton's trick is. Okay? We told you what Euler's trick is. That is that there's an even number of lines coming out of it. What about Hamilton's trick? Answer? Hamilton didn't give us a trick. We don't know of a Hamilton trick. I can't tell you if this one does or does not have it. Okay? I don't have a good trick. The only way I can do this is try every single possible path and see if any path hits every single vertex, yes or no. Trying every single vertex is 1, 2, 3, 4, 5, 6, 7. There are 20 vertices here. That's 20 factorial. That's a long, hard problem. Do you have a better solution? Okay, so how are they related? So far we talked about easy problems and hard problems. Let's go through, let's just recap. Okay? My daughter did the graphics. Ready? Easy problems, hard problems. An easy problem is the Euler cycle problem. Euler taught us this trick, and the trick tells us how to tell if there's an Euler cycle, yes or no. So that's an easy problem. We don't have to try all possibilities. We just have to go through every vertex and see that there's an even number of things coming out. The traveling salesman is a hard problem. The searching, sorting, adding, multiplying, those were easy problems that we started off. Those were very easy problems. Hamiltonian cycle problem, that's another hard problem that we don't have a trick for. Okay? Okay, now here's something a little bit more interesting. Given a statement, and a math statement, okay, I'm not saying it's true or not, determine if the proof is correct. Given a statement and a proof, okay, so this is a math type of thing. Let's say they give you a theorem and they say, here's a proof of it. Okay, now you have to go back to the axioms and see that the axioms are satisfied, etc., and the proof works. So a computer can do that. It can take a statement and a proof and tell if the proof works. Yes, and that's considered an easy problem. All you have to do is go through every step of the proof, make sure that it's kosher. You know, you got this from this, this from this, this from that. Okay, here's a hard problem. Given a statement of a theorem, find a proof. Find a proof. That's very hard. This one is you're given a proof and you want to see if the proof is correct. This one is find a proof. That's very hard. Okay. Thousands of other combinatorial problems. Okay. We have a great book that we teach in algorithms called, I did not write this, Corman lies in her vest. This has thousands of algorithms. All these algorithms are easy. Essentially easy. Easy problems. Okay? But there are thousands of easy problems. There are thousands of hard problems. I just want to point out the difference between the Euler cycle problem and the Hamiltonian cycle problem. Euler cycle, they're both given a graph and they want to know a path. This one wants to hit every single vertex exactly once. I'm sorry, this one wants to hit every single edge exactly once. This one wants to hit every single vertex exactly once. Why is this one easy and this one hard? I have no idea. But it is. This one we have Euler's trick. This one we don't have Euler's trick. We don't have any trick for this one. Okay, so all these we call P problems. P stands for polynomial. All these we call NP. Okay? P stands for polynomial. NP stands for non-deterministic polynomial. Okay? Whatever non-deterministic polynomial means. It basically means, yes, if I had massive super duper parallelism, yes, I can solve it. Problem that can be solved in polynomial time, problems that can be solved in exponential factorial time or less. Problems that can be okay, forget about that. Okay, main point, P is a subset of NP. Okay, these problems can be done in a humongous amount of time or less. These problems need a short amount of time, so P is a subset of NP. Okay? Some technical details. I'm skipping out some things, you'll have to take my class. There are a lot of details that we cannot cover. Suffice it to say that most hard problems that we can describe are not only NP problems, but they are called NP-complete problems. NP-complete they are thought of as the hardest NP problems. They're very, very hard. This means that if you could solve any one of them in a polynomial amount of time, then all the NP problems can be solved in a polynomial amount of time. Let me explain to you. Walking up the steps to this meeting was 4 flights, very hard, old man, okay? The hardest problem in this building is walking up to the penthouse, okay? Now, if I was like you, young and able to do it, walk up all the way to the 6th floor without huffing and puffing, then I can definitely do the easier problem, walk up to the 4th floor without huffing and puffing. So the hardest NP problems are those like walking up all the way. If you can solve those in an easy amount of time, then you can solve these in the easy amount of time. Okay, so let's look at this thing. There's 2 possibilities. There's P is equal to NP, or there's P not equal to NP. That's the question. We know that P is a subset of NP. Okay? The question is it really a subset, or is really P the whole thing of NP? Let's go through it. What this basically says is there's no trick for the hard problems. There are hard problems out there and there's no trick. What this says is, you know what? There are tricks. You don't know the tricks, but there really are tricks. And if you search hard enough, you'll find those tricks. Okay? And then P will be equal to NP. The NP equals NP question is, which way is it right? Are there easy problems and hard problems, or even the easy problems can be solved? I'm sorry, even the hard problems can be solved in an easy amount of time. Okay, great. In the year 2000, so that's the P equals NP question. In the year 2000, there was a rich man, his name is Clay, and he set up the Millennium Prize problems. He wanted to promote mathematics. So what he did was he went to a bunch of specialists and he asked them, give me the 7 hardest math problems. And anybody who solves any one of these 7 hard math problems, I will give them $1 million. Okay? And they went out and these experts found these 7 problems and they said these are the hardest math problems in the world, including number 4, the P versus NP problem. We think of it as a computer problem, but you can express it so exactly that it's really a math problem. And it's probably the easiest math problem to describe. I can describe this to a 3rd grader. I really can. I can describe this to a 3rd grader. Is there a trick, rather than going through all possibilities? Okay? The other problems would take a few hours just to explain what the problem is, let alone solve it. Okay? So they came up with these 7 problems, and one of them is the P versus NP problem. Okay? Somebody, about 10 years ago, solved this problem, the Poincare conjecture. Okay? So there are now only 6 problems left, and we're interested in that one. Okay? But we're going to use these others in a second. Okay, great. So that tells you what the P versus NP problem is. It also tells you why it's important. It's not important because of the stupid $1 million. it'll change the world. If you prove that P is equal to NP, it will change the world. You'll get a lot of fame, fortune, followers, YouTube clicks, whatever. Okay? So, now I told you what it is. I told you that it's considered the hardest problem in math and computers. Okay? And now I want to tell you how to solve it. There's two ways of solving it. Okay. I said it's either this is true or this is true. Let's talk about solving it this way. To show P is equal to NP, very simple. Find a polynomial algorithm for any one of the many problems. Take those NP complete problems, and there are literally thousands of NP complete problems. Like the traveling salesman. Meditate on it and find a polynomial algorithm that solves it. Then all the other problems will collapse and all the other problems will be polynomial. If you can solve that in a polynomial amount of time, then all of them solve, and you prove that P is equal to NP. Okay? Okay? If you prove it, you will make $1 million because of that Millennium thing. Now, you can also do something else, because one of those hard problems was actually finding a proof for the others, for math statements. I told you, if you just give it a statement, to find a proof for that statement is an NP complete problem. Okay? And if you go and you show that P is equal to NP, that means you have an easy way to find proofs of things. So here's what you do. Put the statements of the other 5 Millennium Prize into a proof finder in P. So there's a problem, find the proof. Well, those 7 Millennium problems, the Birch whatever, okay, 1, 2, 3, 4, 5, take these 5 problems, put them into a polynomial algorithm that finds proofs for you. Okay? And what you'll do is put the statements of the other 5 Millennium problems into a proof finder in P. Then you'll make $5 million. Okay, so you'll altogether make $6 million. $1 million for solving the traveling salesman problem, and $1 million for all the other problems. Okay, but I promise you'll make a lot more money because everyone will think you're wonderful, and you'll get a job in a very prestigious university. Okay, okay. So that's how you show P is equal to NP. Do not spend too much time in it. Okay, because it's probably not true. Probably. So, but it's nice to think about it. How would you show P is not equal to NP? That's slightly simpler. Most researchers think that P is not equal to NP. The reason is because they have been looking for tricks for 7 years and found nothing. No one has been able to find a trick. Okay? To show that P is not equal to NP, pick an NP problem, pick something over here, okay? Pick something right over here, and show that it does not have a polynomial algorithm. Now this is a new thing. Show, not here's an algorithm to solve it, show that it does not have an algorithm. Now it's very hard to show things do not exist. Okay? I talk about this all the time in my class. If I wanted to show you a pink elephant, all I have to do is walk outside, get a pink elephant, bring it in here, and you say, here's a pink elephant. It's not hard at all. To show that there does not exist a pink elephant, that's a very hard problem. I have to go through the entire earth at the same time and make sure that no pink elephant exists. That's harder. Okay? So how do we show that, yes, there are algorithms, but no easy algorithms for this? Okay? As soon as you find one problem over here, and you can prove that no easy algorithms there, you got it. Okay? Then you'll make $1 million, but it won't help you. Problem, we don't know how to quantify overall algorithms. I can say for all numbers n, for all natural numbers n, or I could say for all real numbers x. I could do that. I don't know how to say for all algorithms. How do you quantify over algorithms? How do you try and say, okay, this always works? Algorithms are so complicated and they're so messy, we don't know how to do that. Okay, now, 5 more minutes and then I'll let you go eat more. You ready? This is a personal thought. Till now, everything I said was actually true or untrue, whatever, but I didn't make any predictions. Here I'm trying to say my own personal thoughts. Okay, so forgive me or just ignore me. Most people believe that P is not equal to NP. But, and I don't believe either way, but I just want to give you a reason why one should believe that P is equal to NP. Okay? Most of the algorithms that we use are n log n squared, and even n to the third. Matrix multiplication is n to the third. Okay? A few are n to the fourth. And there are even fewer that are n to the fifth. Okay? Now, we teach this book. I don't think there's five algorithms that are n to the fifth. This is an 1,100-page book, and I don't think there's 5 algorithms that do that. Question, why not? Where are the harder algorithms? Where are the harder problems? This is an 1,100-page book, very technical. My students in the beginning hate it, but then they love it. Where are the harder algorithms? Where are the harder problems that demand n to the 6 or n to the 7 or n to the 8? Okay? Not much more. Why? Where are the algorithms? Okay? Why can't we, the human species, collectively think of problems and solutions that are harder than n to the fifth? These are the best and brightest people in the world coming up with algorithms that go into this book. Why aren't there problems that they can solve that demand more than n to the fifth? Okay. We can. The answer is we can. Okay? There are a lot of problems that are practical, and the only algorithms that we know of are 2 to the n or n factorial. The traveling salesman problem is a very practical problem. I told you how to do it. A man wants to visit 100 cities, a very practical problem. Yet, we don't know a practical algorithm for it. We don't know an easy algorithm for it. We know try all possibilities, but that doesn't really help us. What about problems that are n to the 12th, n to the 6th, n to the 12th, or n to the 23rd? Okay. Why should there be such a gap? So look what we have. We have a lot of linear algorithms. We have a lot of n log n algorithms. We have a lot of n squared algorithms. We have a few n to the third algorithms, n to the 4th, n to the 5th, and the rest are exponential. Let's say they weren't exponential. The question is, why is there such a humongous gap here? Okay? And the answer is, maybe there isn't a gap. Maybe these problems do have a solution, and they're polynomial solutions, but they demand n to the 12th, or n to the 20th, third, or something like that. Okay? So that would be an interesting thing. Okay? Maybe there is an algorithm to solve the traveling salesman problem in n to the 17th. I don't know if there is. I can tell you now, human beings aren't smart enough to figure it out, or we aren't until now. Okay? This would mean that all NP problems can be solved in about n to the 17th. We just do not have the brains to find that algorithm. That's an interesting thing. It's not that it doesn't exist, it's that we can't find it. Okay? This would be the question, this would solve the question of the unnatural gap. Why are there n to the 5th algorithms and then exponential algorithms? What about in between? Okay, my friend Camille is here, so I have to talk. He's a computer major and a philosophy major, so I have to talk to him for a little bit. Okay, it also means that the gap is a product of our limited human intellect rather than something external or metaphysical. Okay, in other words, the question is, if there does not exist a better algorithm, ontology, that means existence, does it exist? Or do we humans do not know of a better algorithm? So question, you wanted Hamilton's trick, right? We know Euler's trick. We want to know about Hamilton's trick. Does Hamilton's trick not exist, or are we just not intelligent enough to find it? Okay, so it's a question of ontology versus epistemology. Does it not exist, or are our brains just too stupid to figure it out? Okay? I want to say it's epistemology. That means we just don't know it. But ontologically, there are better algorithms at n to the 17th. Okay? Yeah, I would like to think that there is a solution to the problem. It's at n to the 17th. We can't figure it out. We can't know if it exists. but it does. Okay. That's the only reason why I can think why P is equal to NP. Because I don't like this ontology. I don't like somebody telling me, no, you don't have the right to know this, or this doesn't exist. I like telling me, oh, look, human beings we share 95% of the IQ of the DNA of chimps, and therefore we're basically mutated chimpanzees, so we're not that intelligent. That's a strong possibility. Uh-oh, Camille's angry. No, you agree. We are mutant chimps. That's what we are, right? What's that movie with the Planet of the Apes? It's the other way around. The apes ran things before, and then we became mutants and got a little bit higher IQ, and that changed things. Okay. 2 more slides. If P is consequences of a solution. If P is not equal to NP, I do not see any changes in the world we live in. If P is equal to NP, and we actually found such an algorithm, found algorithms, then RSA, that's what communication is, would be broken. Most internet security would be worthless. All mathematics would be able to be done by a computer. You'd put these theorems into these proof finders, and they would find it in a polynomial amount of time. All mathematics would be out the window. You wouldn't have to take any math classes anymore. There would be no need for quantum computers because a classical computer with these fancy algorithms can do much better than quantum computers. They would be able to sequence drugs for each person differently. You'd come into a doctor, you say, I have a problem. They would look at your DNA like this, find specific drugs for you, et cetera, et cetera. The world would be a much different place. Other possibilities. So we said 2 things. P is equal to NP, P is not equal to NP. It could be that P is not equal to NP, or P is equal to NP, or P is independent of the axioms of mathematics. This is something like Gödel's incompleteness theorem. We don't have the axioms to figure that out. P is equal to NP, and we'll never be able to prove it. That's a possibility. P is equal to NP, and we will be able to show it, but the algorithm is too high for a practical difference. Let's say the algorithm is n to the 50th, and we found this n to the 50th algorithm. But n to the 50th, no computer can run an algorithm as n to the 50th, so it wouldn't make a difference anyways. That's a possibility too. It is known that if P is not equal to NP, then there are infinite, let's forget about that. Okay, how do you learn more about this? Where to learn more about this? From my book, okay? I don't have a copy of it, but here's my book, okay? So this is chapter 5 in my book. This is the hardcover version, the softcover version. It's in 2 Chinese different versions. It's in Finnish, Arabic, Farsi, and Dutch. Gotta buy it, especially the Dutch version. Okay, or the following classes. We take classes in this college, so let's do it. CISC 1002, Outer Limits of Reasoning. We talk about this type of stuff. Analysis of algorithms. We talk about this stuff. Theoretical computer science. We talk about this stuff. Okay. Thank you very much. I just want to say one other thing. This book is the book that discusses these things. Computational Complexity by Aurora and Barak. That's the textbook that you wrote down. Any questions, any unhappiness, any discussion? Go. Well, but Camille, short, and don't.
Yeah, thank you for that. No, yes, not a problem. First of all, they got to induce people with more than $1 million. They got to obsess people with like 100 million to devote their lives to.
If I could, I would.
Yeah. The question that I had was, like, I can never do the math in this, but basically, like adding, like multiplying, if we start with the intuition that these are fundamental limits of knowing or abstraction or the arrangement of the universe or movement, etc., right? Because there are so many paths, so we have to solve it more complexity. Oh well. How do we get about with that starting, if it's not independent of mathematical axioms, mathematically, how would we even begin with that intuition? Like, yeah, it's just more complex, abstractly or ontologically, because it's arrangements, etc. I don't know. I don't do math, but what would you say? Like, that's what it is. That's what my intuition says.
Right. I had a very interesting conversation with a physicist. He's a physicist, PhD in physics, NYU, taught here and there, whatever. A real an intelligent person. And I told him something that every computer scientist knows. I said, it's easy to multiply, it's hard to factor, right? If I give you two big numbers, you can easily multiply them. If I give you a giant number, it's hard to split them into two, and that's where RSA works. He was in shock. What does that mean? That there's a process that we could do one way, we can't do another way? He never heard that before, whatever. Why should that be? Why should the universe be in such a way where it's hard to do certain things and easy to do other things? By the way, it's not in physics, okay? It's very uncommon in physics. I mean, whatever, thermodynamics, whatever. So I have no idea. More questions?
Philosophically speaking, in mathematics we have this thing called a singularity. But could that extreme difficult problem represent a singularity on algorithmic space?
No. So there's no singularities. Let me tell you why. Because if you solve any one problem, you could solve all of them collapse.
Okay.
So it's not a singularity. If you find so there's literally thousands. There's books with lists of thousands of NP complete problems. Biologists get into this with searching through DNA and stuff like that. And any one of them, if you show that it's if you find a polynomial algorithm, every single problem will collapse and become a polynomial algorithm. So that's a shocking thing. You want to say, look, the traveling salesman problem is a hard problem. The Hamiltonian cycle problem is a hard problem. No, there are thousands of such hard problems, and each one is reducible to each other. If you know any other questions, otherwise I'm going
Can you
to.
expand on the singularity?
No, he talked about a singularity. Singularity means just one thing is hard, everything else is easy. It doesn't go like that. If they're not just one easy problem, one hard problem, and everybody else is hard. Either they all collapse or they don't collapse. Anyways, thank you very much for listening to me. Take care.